In the last 6 lectures, we have seen Lebesgue's differentiation theorem, which showed that the derivative is informally a left inverse for the integral for L1 functions. And in this week's lectures, which will be our last topic for this course, we will talk about differentiation theorems, which will establish almost everywhere differentiability for some more classes of functions. So we will see almost everywhere differentiability for functions of what are called bounded variations, functions of bounded variation, and as well as functions which are monotone, so either monotonically non-increasing or monotonically non-decreasing. So these differentiation theorems allow us to take the derivative of functions which are not differentiable everywhere, but they are still differentiable almost everywhere, and we can do analysis on these classes of functions. We will also touch, but rather briefly, what's called the second fundamental theorem of calculus, second fundamental theorem of calculus, which says that if f from a finite interval to r is an almost everywhere differentiable function, in a certain class of functions. So it's not true for all kinds of almost everywhere differential functions, but in a certain class, then the integral of the derivative of f prime, the derivative f prime of f dm, this is equal to f of b minus f of a. Let me just remark here that the goal of treating this topic is not to give you detailed proofs, because usually the proofs will be quite long. So I will only give sketches of proofs and leave either exercises for you to do yourself, or when it's something complicated, then I will give you the right reference for you to go and look it up in a book. So let's come to the definition of functions of bounded variation, which we will treat first. So here's the definition of the functions of bounded variation. So if you consider a function on a finite interval a b, a real valued function, and pick a point x between a and b, a excluded and b included, then we define the variation which we denote by var f ax of f over the interval ax. So this is the variation of f over the interval ax, closed interval, and it is defined as the supremum of all these sums. So the sum of these are the how much f is varying over endpoints of partitions, endpoints of subintervals given by a partitioning of the interval ax. So you take a partitioning t0, t1, tn of this closed interval ax, and then you can sum over all these differences of the function f over the endpoints of the subinterval, and then you take the supremum over all such partitions, and this gives you a quantity called the variation of f over this interval ax. So here note again that the supremum is taken over all partitions of ax. And now the total variation of f over the whole interval a b is simply defined to be var f a b. So again you take the supremum over all partitions of a b and you take sums of this form f t j plus 1 minus f t j, and you sum it over the endpoints of your partition. Finally, the function f is said to be of bounded variation if the total variation is finite. So this is the definition of a function of bounded variation. So now let's look at a couple of examples of functions of bounded variations. So first one is, if f from ab to r is a bounded function, as well as we assume that it is monotonically non-decreasing, then f is of bounded variation. So in fact you can take any partition of AB. So let's say A equals T0 and T1 and so on, and Tn equals B. So if you take any partition of AB, then this sum j equal to 0 to n minus 1 of modulus of ftj plus 1 minus ftj tj, since f is monotonically non-decreasing, this is greater than or equal to 0, and so you can drop the modulus sign. So this is nothing but j equal to 0 to n minus 1 f tj plus 1 minus f tj. But this is now a telescoping sum, and so in the end you will only get fb minus fa, and since f is also bounded, this is less than or equal to 2 times the supremum of mod f x in AB. So we see that if you can take any partition and it will be bounded by this value which does not depend on the partition, and so you can take the supremum on the left hand side, which will give you that f is of bounded variation, because the total variation will be finite. So this is our first example, and we will see that in some sense all bounded variation functions can be described using monotonically non-decreasing functions. Now another example is, if f from A to B, same domain, is Lipschitz, it's a Lipschitz map, which means that there exists a constant m such that the modulus of fx minus fy is less than or equal to m times modulus of x minus y for all x y in AB, then f is of bounded variation. And again one can use a similar argument that we used in the first example and use a telescopic sum to prove this, and I leave it as an exercise to show that this is of bounded variation. Now let's look at a non-example. So a function which is not of bounded variation. In fact, this function will also be continuous function. So let f from 0 1 to r given by fx equals x sine 1 over x if x belongs to 0 1 and 0 if x equal to 0. So this is also sometimes called the topologist's sine curve, and in fact this is a continuous function, so f is continuous but not of bounded variation. So I leave it to you as an exercise to show this. The point here is that this factor sine 1 over x has a lot of high oscillations, and which means that when x goes closer and closer to 0, there is a lot of wiggle in the graph of this function fx. So the graph of the function fx looks something like this. So when you go closer and closer to 0, so there is a lot of wiggle near 0, but still the function f is continuous, and the limit as fx goes to 0 from the right hand side is precisely 0, even though it is not well defined. X sine 1 over x is not well defined at 0, but still the limit exists, and this makes the function continuous. But this oscillatory nature of sine 1 over x breaks the bounded variation, because there are infinitely many ups and downs in this curve as x goes to 0. So I like you to make this argument precise, prove this, and in fact show that x to the power a sine 1 over x to the power b is of bounded variation if and only if a is greater than b. And I should add here that both are taken positive. So it is a bounded variation if and only if a is strictly greater than b, and both are positive. Now we come to the first important property of functions of bounded variations, and this is given by this lemma, and this says that the bounded variation functions can be expressed as a difference of two bounded monotonically non-decreasing functions, which can be defined from the given function of bounded variation. So I'm going to use this abbreviation MND for monotonically non-decreasing because we are going to use it very often. So the statement of this lemma is as follows. So if f is a function of bounded variation on this interval AB, then there exists bounded monotonically non-decreasing functions f1 and f2 such that f is the difference of f1 and f2. Of course, as a corollary, we have that a function f is of bounded variation if and only if it is a difference of two bounded monotonically non-decreasing functions, because the only if condition is given by this lemma, and the if condition follows because our first example shows that any bounded monotonically non-decreasing function is of bounded variation. So if f is a difference of two bounded monotonically non-decreasing functions f1 and f2, then both f1 and f2 are of bounded variation, and it's not very difficult to show using the triangle inequality, usual triangle inequality, that the sum of two bounded variation functions is again of bounded variation. So here use that if f equals to f1 minus f2, where f1, f2 are bounded monotonically non-decreasing functions, then both f1 and f2 are of bounded variation, and thus f1 minus f2 is also of bounded variation. So the total variation of f1 minus f2 can be estimated by the total variation of f1 and the total variation of f2. So I leave it as an exercise again for you to thresh out the proof for this corollary. But now let us look at this proof of this lemma. So for this, let's fix a point x in AB, and we also fix a partition P given by T0, T1 and Tn of this interval Ax. So this is a partition of this interval Ax. Now we define two sets I plus P. So I will only denote it as I plus when the partition is evident. So this is the set of all j in 0, 1, 2 up to n, such that ftj plus 1 minus, well, ftj plus 1 is greater than or equal to ftj. So these are the subintervals of the partition on which the on the rightmost endpoint has higher value, the f has higher value on the rightmost endpoint than the left endpoint, and similarly I minus, which is I minus p, this is the collection of all these indices j such that ftj plus 1 is less than or equal to ftj. So this means that f takes lower values on the right endpoint than the left endpoints. Okay, so now we define the positive variation, which we denote by var plus f ax. So this is defined as the sum over all partitions of sums taken over the positive I plus. So these are the indices where you get positive values for the difference ftj plus 1 minus ftj. So here you can write ftj plus 1 minus ftj, and so this supremum is taken over all these partitions of the interval Ax. Similarly we can define the negative variation denoted by where minus ax of f, and this is defined as with a similar formula. So you get j in I minus of p minus f tj plus 1 minus f tj. So here there is a minus sign for each of the terms in the sum. So this is where minus of f ax, and this one was where plus of f ax. So now I claim two things. Claims that first is that both where plus f ax and where minus f ax are bounded and monotonically non-decreasing functions on AB. So this is the first claim, and the second claim is that we have the formula fx minus fa is equal to where plus f ax minus where f minus ax. So here, so this is small f. So here, of course, if assuming both these claims are true, then we immediately get the statement of this lemma, because this implies that f is equal to where plus f, so fx is equal to where plus ax plus fa, so this is one function, minus where minus f ax, and both these functions are bounded and monotonically non-decreasing. So then we would have expressed our function which was of bounded variation as a difference of bounded monotonically non-decreasing functions. So it's we are only left to show these two claims, where first is that both are bounded and monotonically non-decreasing on AB.